All right, I'm recording this session. So you all need to agree that this is being recorded. We can do that. So if you remember, when we talked about the controller, one of the goal was to make sure the system performs the way that we expect. Now, if you think about, we can also say that in terms of error. So if the system drives the error to zero or to a very small amount, then we will say that the controller is performing well. But then what is an error? So the error is the difference between the desired value that you set and the current value that your system, for example, here, the joint that you're looking at is. So the position of a joint, for example, the desired position is 45 degrees. You send the command and then the actuator is turning and then the joint comes to a position. You'll measure that. Let's say that is 42 degrees. The difference between 45 and 42 is 3 degrees. So that's the error. So theta E is something that for joint control, we will create, for example, for the position of the joint. So again, this is position error. It is important because we have velocity error as well. So we have to look at the velocity. Theta is the joint error or the joint position error. Then theta D is the desired position and theta T is the actual position of. The purpose is to drive that to zero. However, we might not be able to drive it to zero, but we might be able to decrease it to a very small amount that is acceptable. So what is acceptable in aerodynamic is really important. Now, usually to check and evaluate how our controller works, we give a non-zero error value at time 0, and you want to observe how quickly the controller responds and how quickly reduces the error, the initial error that we give to 0 or to that acceptable value. So an ideal controller will drive the error instantly to 0, right? But then again, we are a little bit far from ideal because we always have losses in our system, and usually it takes time. For example, when you start the motor to go to 35 degree or a position, you're supplying the voltage and current to the motor, it has to start turning. So it does not go immediately. So we don't usually see such movements, right? As we talked before, we're going to see this is 0, and then we're going to ramp up to the value. So the purple here is our desired value. Let's say theta desired, and the red is how fast our system can get to that. Now, if you remember, I talked about my car, my husband's car, and I think Jess's car. Depending on the motor, how good the car is, we can decrease this time, right? So let's say we call it TS, settling time. Now, when we design a controller, we want our controller to go to this 2% settling time, which is 98% of our desired value, as fast as possible. Now, we can't design a very fast controller and put it on, let's say, my Jeep, and expect the motor to handle that and go from 0 to 60 miles like a Porsche would. So you design the controller, your controller should match your system. So you can't put a very fast controller on a system that is naturally slow. That's why we always look at the natural response of a system first, then we design our controller. We usually call this portion the transient response, because it is the time that it takes from 0 or the initial condition to what the desired value. And this area where the system stays fixed, we call it a steady state. So any value here, for example, this is your steady state value. So this is what we're talking about. Now, if we are looking at the error of the system, right? So, and then we have this, so error based on time, and then we get to this point, this becomes the steady state error, or ESS. So you will see that I use that a lot, and you can see it here. This just means that the error reached a value that does not change after that. Now, if you remember, our systems are second order, right? We decided that we are going to use second order system. If the system was higher order, we are going to change the system to a set of second order system. Now, the error of that system is also second order. So we expect to see similar kind of response from that. So if you remember, we said we are going to give the error at time 0 a non-zero value, and we want to see how fast the controller will drive this error to 0 or the value that we expect, to a steady state value. So here are, so this is a second order system. So theta double dot plus theta dot plus, sorry, E double dot plus E dot plus E equal to, let's say, 0 or some value. So here, for example, 0. So this is a second order system. So we expect to see a response that looks like that. Now, if we have initial condition, we start from here, and this amount is the overshoot, the time, the error response that initially went over our steady state value. This is the steady state error. And then now a good controller does a few things. One, little to no steady state error. Right? So we prefer if we had smaller overshoot. So we do not really like overshoot that look like this, right? So now when we say little, this also depends on what does little mean for that system, obviously. So little to no steady state, sorry, that first one was about a steady state. So we either want this is steady state be 0 to, or be very small, so it goes to 0, little to no overshoot. So you usually see percent overshoot, and then a short TS or settling time, which is that 2% settling time. And the reason is that we want it to be faster. So we want to be closer or to, so we want to get to our steady state as fast as possible. But again, we can design a very fast controller for a slow system. It just wouldn't work. Does that make sense? We also kind of review all of that on Friday. So I wanted to give you, like, kind of finish that lecture. Are there any questions? If you don't answer, it means no. All right. So I can, this is difficult. I forgot how difficult it is to teach online because you don't see anyone. All right. So I put together a slide that why feedback systems are desirable. So yes, feedback control is desirable because it can dramatically improve system stability, disturbance rejection, and tracking. So when we say disturbance rejection, what do we mean? And when we say tracking, what do we mean? Does anybody know? Either you can type in the chat or you can unmute yourself.
Dr. Z, I think when you say disturbance, I believe, like, say there was you're trying to stay at a desirable value, like it's desirable temperature, and then for some reason it like gets hotter in the room, then you can go back to stability.
Right. So your system or your controller will be able to deal with that disturbance, so can reject it or bring itself back to stability. Correct. So when we say tracking, we want to improve the tracking of the system. What do we mean by that? Adam, can I volunteer you?
Yeah, you can volunteer me. It's the ability for a system to follow an input that's changing in time.
Okay, so correct. So when we say tracking, remember that we have a desired state that we want to get to, right? So we want to always be able to follow that. So if we are saying that, okay, our theta desire was 45 degree, our system should be able to track that. And then now if the next desired state is for 80 degrees, our system still should be able to track that. Any state that we want to follow and any reference signal that we are giving to the system as an input, we want to make sure that our system is able to follow that. All right. Now, we also want our system to be stable. A mathematically speaking, you can think of it as keeping all the poles in the left-hand side. So when I say mathematically, in terms of the control. So if you remember, poles was the putting the denominator of a transfer function of your system equal to 0, and then find all of those s equal to those numbers. So those are your poles. We want to be all in the left-hand side, making sure that our system always reaches some steady state. Now, sometimes we might see this. So let's say your desired value is supposed to be here, theta d, and your system does that. So this is your steady state error. So this system is stable because it reached a stable value at here, right? So this is theta steady state, but it is not tracking your input. It has a huge steady state error. So system could be stable, but it could but there is a chance that the system is not tracking your reference signal. Then you will design a controller to bring this up. So with controller, you could see something like this green line, just still within a stable system. An unstable system would look like this. Let's say it keeps going up. So you see that it's unbounded going up. And if you remember from last class, I gave you this example. A system can be stable like this, like it is, well, actually unstable, but it's bounded. So it does not, this is not in a stable as time goes. It's still, this is a case of stable system, but it does not reach a steady state. All right, and we can fix this system by manipulating the control. If you remember control, you know that there's a pole at 0 and you need to fix that if you see something like this. It does not apply to what we are going to talk in this course, but if you're familiar with control, you should be able to understand the system behavior by looking at this response plots. All right, so back to our trusty robots. Now, when we talk about controlling the robots, we talk about two things. One, operational space control, which is your task space. And we are in Cartesian, right? Here, we want to control the end effector position and orientation. We have two ways of doing that. One, using potential field. We will define a potential function, okay? And then we get the gradient of that, and then we find tau equal to J transpose of that F, that function. Or we could write the dynamic equation of the end effector, right? Which was your equation of motion, and use inverse kinematic to control the robot. The other method for controlling a robot is your joint control, joint space control. So in this case, we will define a vector whose components are translation or angular displacement of our joints. translational and angular displacement of the joints. So the difference is here, we will control each joint, right? And then we check if we end up where we wanted. So we are basically checking, well, this one. We're controlling if each joint is supposed to go where we decided. Here we're saying, no, we're just going to look at the end effector. And we know where the end effector is at all time. So we have two methods of doing that. All right. Now, looking back at what we learned so far, we want to know how we can design a controller. All right. So we usually look, let's see if we have, so we usually think about, when we think about in control, we're thinking about, okay, I have a desired position that I want to go there. I want to grab this cup, right? And I want to drive this robot to go and grab the cup and then move it from point A to point B. So since we have a desired position, to reach that desired position, we can use inverse kinematic and then decide what should be the angle of each joint, right? So we have a desired position, we apply inverse kinematic, IK, and say, okay, we got a desired position for each joint. So desired either angle or if it's prismatic, like the translational position. Then we are gonna send commands. So these are the commands to each joint separately. Okay, we look where you are, okay, wherever the joint is at its home position, and then we drive it for delta Q to reach to that Q desired. Now, so for a joint to move, we need to send a command to its actuator, right? So each actuator has its own controller inside of it, is a driver. So the actuator will drive the joint to where we said, and Q1, Q2 to Qn, right? So we get a vector of Q, which is supposedly is all the joint positions, angles or position, translation or position. All right. So, and we have the knowledge of that because we know how to calculate inverse kinematic. We just need to give them some desired value and then get the position of each of the joints. Now, is this an open loop or closed loop system in the big picture? So let's say this is all joints. So each one of these has its own subsystem. We are not looking at the subsystem. We are looking at this big picture. So is this big picture an open loop or closed loop? If everyone types in the chat, the answer. All right. If you said open loop, you're correct. Because for this general system, we're giving an input, like a reference input that we desire. It goes through some blocks and it gives us some joint values, right? We are not checking if these joint values are what we asked for. If we did that, then we can close that loop. Now, going back to the concept that we learned, if we know the set of angles, right, that each joint needs to go, and we want to calculate the position of our end effector, right, what method we can use? So I have all the joint variables, and I want to know where is the end effector position and orientation. What method I can use? Based on what you have learned, we can use forward kinematic, right? So using forward kinematic and inverse kinematic, you can control your robot. So first, using the inverse kinematic, you can go from desired position to possibly the joint variables. Now, we will send the command to our actuator, and then so we are moving the system. We don't know if we got where we wanted. So we have to calculate the positions again and compare. Then if there was any difference in the position, we can apply our inverse kinematic again now for this little distance and shift everything, move everything a little bit and check. So our robot manipulator at configuration theta, at where it is right now, we can find the position based on those theta we have. So first, we have some initial values for each joint. We can calculate through forward kinematic, where is currently the position of our end effector, because we might not always be at home position, right? Then we check that position against a desired value that we have in mind. That value delta X is the changes we need to make to the system so that the end effector gets to where we want. Now that translates in finding the changes in theta for each joint, right? So this J inverse, this is a mapping between the position of the end effector position to joint variables. All right. Now, this is your control law. Control law tells you that wherever your joint variables are, your initial theta plus the amount of change that you need to apply to the joint to get to your desired position. Why we are using theta as our control law? Because that's what we can directly change. These are our actuations, right? So this theta is a vector, like of each joint. We can manipulate each joint's position and get the whole system moving to a new state. Then we calculate where is the position of end effector in that state. Do the comparison here. And then if there was any error, this delta X is your error in position. If there was, then we go through that again until this error is either 0 or something that's acceptable, which is if it's kind of millimeter difference, if it's centimeter, if it's meter, depending on what is acceptable for our operation. Does that make sense? How the whole feedback control system works? All right, hopefully it makes sense. Now, this is the concept of feedback control. Now, to do this, we need a controller block here. We need a controller. I'm gonna write it this color. So we need a controller that does that for each of our joints, right? You have a lot of options. There are plenty of options for what kind of control scheme you want to use. One of the simplest ones in terms of control law, how to change things, is a PID controller. Some of you might have heard of what PID is, some of you might not. PID, the benefits of PID controller is that the control law is easy. We already have the control law here. This is your control law or control signal. We know what is made of. The difficulty is that you need to tune the PID controller sometimes, and it takes for a while to tune that to the value that is desired for us. All right. P, I, and D represents proportional, integral, and derivative. So this is for P, I, and D. PID controller looks at the error of a system in the present, past, and future. So the element that is in the present proportional is multiplied by a coefficient called K, well, KP usually. So proportional is KP, I'm gonna add P here. So we multiply that by amount of error directly. So how much error do you have? I have 10 centimeter error. Okay. Multiply by a value that drives this to 0, right? Or to 1. Then you will have an accumulated error that is caused by all the error in the past. That's the integral. We multiply that by Ki, and we get the integral of all the error, which is the area underneath the curve. And remember that you plotted the error, right? So that's the second term, that's the integral term, sorry. Then the third part is that if our system continued this way, can we estimate in the future what kind of error we have? So that is the tangent of our curve in the future at time t plus td, or a time in the future, right? Anything plus t. Now, the tangent we can calculate using the derivative. dE, which is et, the error, the derivative of error with respect to time, and that is usually multiplied by a value called kd. So all of these have a coefficient. So PID controller is basically made up of these three elements, these three parts, right? Proportional, derivative, and integral. We have information about the error, the integral of the error, and the derivative of the error, but we don't know what kind of coefficient we need to use to drive this error to zero. Okay, so when we put them together, we get the control signal or our reference signal that we need to manipulate the system based on that. For that signal to be able to drive the error to zero, we need to find the values for these three. Usually we use a trial and error method to find that. All right. If you work with PID controller, you know that tuning the values is not an easy job. I think I shared a lecture of my control course with you on how to tune the controller value. So that's an extra like material, so you don't have to like do it for this course. We're going to use other means to kind of guesstimate, like more educational guess of where we have to start with tuning these values for our application. But in general, if you need it, guideline, I've shared that slides, I think, with you, that lecture with you. Now you can, so that was in time, right? So here we introduce the control law in time. You could also show this and write this control, PID control in Laplace domain, which is a lot more useful because then you can use Simulink in MATLAB and tune your controller. There is a great toolbox in MATLAB that can help you to tune the controller. Again, these are extra material. You won't use Laplace domain, but if you need it, you can find it in MATLAB or your control course if you had. Now, PID control is called a 3-parameter control. You will have different, the 3 parameters are P, I, and D. From these three, you could have just a P controller, a PI controller, a PD controller, or PID. You cannot have I controller or D controller separately. You always have to have a P. Now, P could be 1, right? So when it's 1 times the signal is the signal itself. So you're not changing anything. So if you needed to use an I to accommodate for the accumulation of the error in the past, you can say, okay, my P is going to be 1, my I going to be 0.1, for example. So you have to use P in all of them. All right. Okay. Any questions before I go to an example bot or like a example robot? No questions? All right. So, let's see. Nothing on Discord. For our robot manipulators, I'm going to drive the control law. All right, and you'll see that it will look like a PID controller. So this will help you to understand how to design controller for your manipulator robot and why the PID controller, it works for it. All right. So let's assume you have a 1 degree of freedom robot that has a prismatic joint. All right. This is the end effector, where the end effector is the end of the prismatic. We are at some initial value position. We are applying the force. We want to control it. So we have a input. So this is our input. We are applying an input, and we want to bring that the end effector to this desired position. All right. So here the equation of motion will be mx double dot equal to that input. I'm going to use potential field that we discussed here to drive my control law. To do that, I'm going to create a potential function, right? Let's imagine that you apply a force to this prismatic joint and then you let go. So you push this and you let go. So the robot will start moving from here. And then if you don't stop it, it's gonna keep going. So if you look at that, so you start from some x0 position and you want to go to xd, right? So x desired. We start from some force here, and then we get close to our x desired, but since you are still applying the force, our position is going to change. So we are going to end up somewhere here, depending on how far we apply the force, right? If we don't stop the force at our x desired. So stopping the force as x desired is another kind of input, right? Because you're applying a pause. So maybe it's better to just say that if we pushed it, it's some f, and it will keep going. Now, so we're going to call this our potential function. So for where potential function is greater than 0, our x is not equal to x desired. For one place where this is at 0, so I didn't plot this very well. Where we start here, we go to 0. So for one position at 0, our x is equal x desired. So we know that for one instant, our end effector will cross our x desired. All right. My Vx, I introduce the potential function to be 1/2 kp x minus x desired squared. So this is my delta x, right? So this is how I introduce my potential function. And if you're familiar with this form, you know that if you plot it, you will get some curve like the pink curve that I draw here. So this is 1/2 sum k times x minus x desired square. That's the plot of that curve, right? So from the potential theory, we gonna say our input is the gradient of this Vx. So f becomes partial of v with respect to x. All right. So if that our potential function f, the input is going to be partial of that potential function with respect to x, which is the state that we're changing, right? That desired value we're changing, that state. So if I wrote f partial with respect to x, 1/2 kp. So this, I'm putting kp because you already saw this is the proportional, but it could be a k, a coefficient that you're gonna need to define what it is. Minus x desired square. If we calculate that, is negative kp, or that coefficient, times x minus x desired. All right. Now, this is the input that you need to apply to your system to make sure that at one point, the end effector will cross your x desired. So the system itself, the dynamic of the system is mx double dot, which is equal to the input that we apply. So the external force is negative kp x minus x desired. All right. If we rearrange this, is mx double dot plus kp times x minus x desired equal to 0. At one point, we are going to be at our x desired. This is your position error, right? And this is the position gain. If x minus x desired is 0, mx double dot is equal to 0. All right. So now this is our P controller. So we artificially created an expression and added, so this is artificial, to our, sorry, my artificial doesn't look good. Added to our dynamics. So that force, external force, is being added to the dynamic of our system, so we can ensure that our end effector will cross the desired position at one instant. All right. So what is that KP? We need to decide how fast that is going, right? Depending on what is x minus x desired, how big or small it is, we can decide about our KP. We usually pick one and then draw and see how far we are. Then we change that KP until we find the desired KP value. Now, we see that through here, as you saw, we are not sure what's going to happen because since we are not stopping our system, so we're not stopping the F, so we could go from some position, right, to, let's say, if this was our X desired, we are keep oscillating about that X desired because we keep crossing that and trying to come back, crossing that, change the KP, keep going back and forth. We never stop there. So this is still a stable system, but it's bounded because it goes between two values. Now, to make sure that we have, we stop at our desired position, we can define another potential function. All right. This time, to achieve the stability, we want to look at the velocity, because to stop at x desired, what does it mean? It means that the velocity of the system has to be 0 at that point, right? So if you think about some x dot, which is the velocity, we need to introduce a force that will be equal and opposite direction applied to the system at that x desired position, so the system will stop. So this Fs transpose time our x dot will be 0, less than 0 for all the x dot that are not 0. So when the system is moving, then we can say that, okay, our Fs is some kV value times x dot. If we apply, if we change this kV, if we manipulate it, we can decide about the value of this Fs that controls the velocity of our system. Now, previously, we had our control law was negative Kp x minus x desired. Now we are saying we need to add a force that can control the velocity as well. So our F, or we can say our F final Fs, would be our Kp x minus x desired plus this velocity part, negative Kv x dot, right? So this is your velocity control. This is your position control. Now we can ensure we get to our desired position and we will stop there. Now, if you remember our system dynamic, we said is mx double dot. So for depending on the system, because this is just a prismatic joint and we have one body, so it's just mx double dot. But if you had multi-body, then you already know how to calculate the dynamic. So the left-hand side of your equation, of dynamic equation, is this dynamic of the system, right? So this is equation of motion. We will say equal to Fs, or our control law. So now the external forces are the forces we apply to the system to control its dynamic. Now, if you look for this example, mx double dot will be negative kp x minus x desired kv x dot. Now, if I bring all of that to one side, I'm going to use a different color so you can see the difference. I'm going to use blue. I'm just bringing plus kp x minus x desired plus kv x dot equal to 0. Again, this is artificial, which is your control law, right? This is artificial system that this only job is to control the system, to drive the system dynamic, the system behavior to what we want. This is your control law. This one is your whole system after applying the controller to it. So when we say apply controller, we created a new system that has the control part in it, and the dynamic, and it is written that it matches the dynamics of their system. Now you see that now we have a full second order system, mx double dot plus kv x dot plus kp x minus xd. Now things that we don't have is this guy and this guy, because these are controller, they're coefficient, we didn't know what they are, we just say kp and kv. Now, to ensure that the system behaves the way we want, we need to decide what these values are. All right, so we kind of need to tune for this value. That's what it's called tuning. Now you might say, okay, how do we tune? What does it mean? This goes back a little bit to how much you know about second order systems, but we can write a second order system. If you remember, we can write the standard form of a second order system is x double dot plus 2 zeta omega x, well, yes, 2 zeta omega x plus omega square x dot equal to 0. Well, you can bring this here, bring this there for the continuing. Looks correct. All right, now these are the values that are related to our system. All right, so are you familiar with what omega and zeta are? Anybody? Damping ratio for zeta, and what is omega?
Natural frequency.
Natural frequency. Now, if you look at a standard form of a system, so omega, omega is the natural frequency of your system. Zeta is damping ratio of your system, right? Now, when we add a controller, we kind of, so if you look at here, we just created this controller, P controller and D controller, right? So because it's multiplied by X dot. So this is a PD controller, proportional derivative. If you look, these two are, so if we divide them all by m, here, I actually have it here. If we divide them by m, we can compare this form with the standard form, right? So kV over m is omega squared. I'm just comparing it with the standard form, and 2 zeta omega divided by m is kp, well, sorry, just following the same. So kp divided by m should be equal to 2 zeta omega. All right, now from here, if we know what is the desired damping ratio of a system that's being controlled, and what's the frequency of that desired system, then we can find our Kp and Kv value from it. So we can reorganize, as zeta will be Kv divided by 2 square root of Kpm, and omega is the square root of Kpm. So from first this one, if we know what is the desired frequency, we can guess, we can find a value for Kp. Then we can plug it in the other equation and then find a value for Kv. So that is our first guess for our PID coefficients. We plug it in, we plot the response, and we look if this is something we wanted. If it is a slight difference between, we can then adjust from there. So know that for PID controller, you always have to tune, but where to start, these 2 points are the best educated guess to start with. On Wednesday, we are going to solve an example, all right, and utilize what we learned here, and you'll see that there will be a desired value for frequency and damping ratio, and we're going to design a controller for it. I think your homework also is asking about that, right? Adam, you already solved the homework, right?
Yeah.
So, okay, so that's all for today. I know it was on Zoom. I couldn't see everyone, but hopefully you got the gist of what's going on. On Wednesday, when we solve that problem, we kind of go back to this to review, and hopefully it will make sense. Are there any questions for me?